So, for the paper section of episode 4 of the Raised Beaches podcast, I'm only going to highlight one paper. And the reason for that is I'm a co author on this paper and I have a bit to say about it. And this paper, which was led by Karla Rubio-Sandoval, is entitled Quaternary and Pliocene Sea Level Changes at Camarones, Central Patagonia, Argentina. And this was published in the December 2024 issue of Quaternary Science Reviews. So, first off, I've discussed this in past episodes, but in 2019, I went to Patagonia to participate in some field work to determine past sea level changes in Patagonia and Argentina. And I participated in this field work, and it was a great experience. And one of the places we went to was a village known as Camarones. And Camarones has a big sign that says it's the national capital of salmon. But if you know Spanish, Camarones actually means shrimp. So one of my cousins said, "Oh, did they run out of Camarones? Why are they the capital of salmon?" And I have no answer to that. But anyway, we went to do these surveys as part of the WARMCOASTS project, which was led by Alessio Rovere. And this was funded by the European Research Council under the European Union's Horizon 2020 Research and Innovation Program. And the purpose of the WARMCOASTS project was not simply to collect new relative sea level data. It was actually to go back to sites that had been surveyed before and try to get more precise measurements using modern techniques. So that is why we went to Camarones. So the sea level deposits, the deposits past higher sea level have been well studied, but we went back with a GPS and we collected more samples to get more precise age constraints. So that is why we went there. So Camarones is located in central Argentina, and of course on the Atlantic side of South America. And if you've never been to or if you don't know anything about Patagonia, it's kind of a desert. And because it's a desert, these shoreline deposits, which were deposited hundreds of thousands of years ago, and in one case much longer ago, are quite well preserved. So because of the preservation, it's been the subject of study for going back a long time. Like Charles Darwin went there, and he didn't specifically study at Camarones, but he did study these raised shoreline deposits in different places. You know, this is the Raised Beaches podcast, so it was interesting to go to these raised beaches, and the specific location at Camarones is interesting because it has evidence of shoreline deposits, raised beaches, and whatnot at 4 different time periods. And because we're far away from the west coast of South America, we would not expect tectonics to be a major contributor to these raised beaches. Like if you go to the Chilean side of Patagonia, you find shoreline deposits, tens to hundreds of meters above present, which are much younger than the deposits that we studied. So this is we're going into this with the assumption that tectonics are quite minor. One of the things that Karla was working on is to determine what is known as the indicative meaning of beach ridges. So Some of the shoreline deposits that we study here are beach ridges, and what a beach ridge is that they're basically a deposit that is pushed on shore by the action of waves during storms. So these usually will form a little bit above sea level, but the precise position of sea level relative to these beach ridges was not well established before this study. So basically, what we did is we calculated the statistics of the wave heights, so going back a couple of decades using satellite measurements, and then used a modern analog of where you find shells on the modern beach ridges, and was able to calculate a relationship between where you find shells in a beach ridge versus where sea level is. And then you go back to these ancient beaches, and you find the elevation. You measure with GPS the elevation of where these shells are found, and then you can tightly constrain what the sea level was when these beach ridges formed, and you can determine the relative sea level changes. So, in the field work we did, we went with the GPS and measured these where these occurrences of these shells were, and also different features in these deposits. And we collected some shells, and it's really interesting because these deposits are very gravelly, but you'll find these like perfectly preserved shell fossils in them, and it's really amazing that you can have a situation where you have this gravel, but then the fossils were not destroyed during the deposition of this gravel. So there's so many shells. As a kid, I was obsessed with fossils, and I mentioned that in the introduction that I love fossils, and it was pretty cool to see all these fossil shells. So collecting these shells, you can find the age of the deposit by measuring various properties of these shells. So the past studies use techniques known as uranium thorium dating and electron spin resonance, and these two techniques sort of rely on measuring the amount of uranium in the shell, and but the issue is that uranium can leak out of the shell, or it can get incorporated into the shell after the shell is or after the mollusk dies. So you have to make a lot of assumptions about how much uranium is going in and out of the shell over time. So the uncertainty on the ages is quite large. So instead, we were using a technique known as amino acid racemization, and we were applying it to a species of mollusk known as Amyghinomia antiqua. These Latin names are kind of a mouthful, and but these kind of shells are found all along the coast of Argentina, and you find them in the shoreline deposits of different ages. So ideally, with amino acid racemization, you want to use the same type of the same species of shells, and what this is an amino acid is an organic molecule, and basically after the mollusk dies, certain types of amino acids will change its form, and this is dependent on the amount of time that is elapsed and the temperature conditions, and based on the ratio of different types of amino acids, you can determine a relative age, because this relationship in changing the form of the amino acid molecule, it happens in a very regular way. So yeah, you can use this to determine if the deposits are of different age. And yeah, we use this to complement these other dating techniques that have been applied. And when we checked the amino acid racemization results, we compared, of course, modern shell, like a shell that we found on a beach right now, and compared the ratio of these different types of amino acids. And yeah, we basically, we know there are 4 different ages of the deposits, and yeah, we can definitely tell that there's a difference between the ages of the second and third highest beaches relative to the Holocene beaches or shoreline deposits. But what was interesting is that the second youngest set seems to have a much broader range of ratio values, and this could possibly indicate that during the period known as marine isotope stage 5, there might have been 2 periods of relatively high sea level, and that introduced shells of different ages into the same deposit. So now I'll go into an overview of the 4 different deposits, starting with the one that has the highest elevation and is the oldest. So the highest one is Pliocene in age, and this was investigated in detail by Rovere et al. 2020, and they had to use a different dating technique, but they calculated that this shore platform probably formed between 4.7 and 5.2 million years ago. And based on the elevation and the geomorphology of this deposit, they inferred that sea level was, the relative sea level was 36 meters higher than it is now. And this seems kind of high because based on what we know about ice volume, it seems unlikely that global sea level was 36 meters higher than it is now. So they infer that there's a component of glacial isostatic adjustment and also dynamic topography, which I talked about in the sea level episode, or in the first episode about raised beaches. So yeah, basically there has been some level of uplift here in the past 5 million years, but it can't be more than maybe 15 to 25 meters. The second highest and the second oldest beach has an inferred paleo sea level of 14.5 meters higher than present, and the age of this is a bit ambiguous, but based on the information we have, it happened between 300 and 420,000 years ago. And this time period encompasses 2 interglacials known as marine isotope stage 9 and marine isotope stage 11. And so marine isotope stage 11 is associated with the warmest conditions and in some places the highest sea level that has happened in the past million years. So based on that, we sort of might expect that this is probably from that time, but some of the age constraints seem to suggest it's actually young or more recent than that. So that'll be the subject of some glacial isostatic adjustment modeling. So the second youngest is in marine isotope stage 5, and like I mentioned, there's the possibility that there might have been 2 periods of high sea level during this time. So marine isotope stage 5 happened between 80 and 130,000 years ago. And the period with globally high sea level is the last interglacial period, which was 115 to 130,000 years ago. So it seems obvious that should be the high period, but based on the amino acid racemization results, it seems like that could have been one period, but there's also the possibility that in 80,000 and 100,000 years ago, there was also relatively high sea level, and maybe there's some shells mixed with this. And based on the deposits that we measured, the relative sea level of this deposit is 8.7 meters higher than present. So it's about I'll talk about this in a second, but it's not so much higher than the high stand in the Holocene. So that also might give a bit of indication that this younger part of marine isotope stage 5 might have been able to get to this level. And it's this 8.7 meters seems to be on the higher end of the estimates of last interglacial sea level high stand. In the Holocene, we were able to get some shells to radiocarbon date the highest part of the Holocene high stand, and based on those radiocarbon dates, it seems that the high stand happened between 2,600 and 3,400 years ago, which seems pretty recent. So around the world, the Holocene high stand tends to happen like 5,000 to 6,000 years ago, and even along Patagonia, it seems to be a bit earlier than that. But what's interesting is that the Holocene beach ridges, which are very different color than the older ones because they're much more recent, has an inferred sea level high stand of 6 meters. So what it's suggesting is that there's been a 6 meter drop in sea level in the past few thousand years, and the 6 meters is only 2 meters lower than the MIS5 sea level high stand. And the reason why the high stand is so high in Patagonia, and this is true along the entire coast, is a result of glacial isostatic adjustment. So basically what happened is when you had the ice sheet pile onto the North America and Europe, that affected the Earth's orbit and also changed the Earth's gravitational field a bit. And when that ice melted away, of course, the water initially flowed to the southern hemisphere, and as the Earth was rebounding after the delayed isostatic rebound, some of that water goes back, but it also was changing the rotation of the Earth a bit, and this effect is quite strong in Patagonia just because of where it is relative to the ice sheets in the northern hemisphere. So I did some modeling of this, and other people have also done modeling of this, and it seems to confirm this idea that yes, the high stand in the Holocene and probably the last interglacial is a result of glacial isostatic adjustment. And right now, Karla, who's the lead author of this, is working on a broader database of past sea level changes in South America, and we'll be able to get a much better pattern of the changes due to glacial isostatic adjustment and be able to model that. And that's, of course, something that I plan to do in the future. So stay tuned. Next year, there will be another paper coming out on this topic, and we'll see about modeling the sea level changes in more detail. So that's it for episode 4 of the Raised Beaches podcast, and I'll see you again in 2025.